Okay, so let's begin the session. Hello guys, welcome all of you to one more live problem solving session for the course Fundamentals of Semiconductor Devices. Just to introduce myself again, I'm SOHAM LAKHOTE, currently a 4th year Ph.D. student at IISC Bangalore, and my research area is in mostly the domain of the analog and RF circuits, right? So now this will be the organization of today's session. First of all, we will have a first part, then we will take a short break and we will resume the session after our short break. And just for the formality, all the lectures are being uploaded to this YouTube channel, and in the description section of each video you will be able to find the lecture slides for that particular lecture. So and these lectures are also there, the link for these lectures are also there in the course page. There is a tab called as the live problem solving session, so in that Excel sheet you will be able to find all these lectures. Okay, so now coming to what we have seen in this week was mostly regarding the solar cell and the photo detector, right? So now the first the way the session began was, first of all we studied the semiconductor and the photon interaction, and after that we studied the solar cells, we looked at the few parameters, and after that we moved on to the concept of the photo detectors and the photodiode, right? So we will follow the same procedure exactly over here. We will just have a quick overview of the concepts that we have studied so that it will help us to solve the problems for doing this session, right? So now let's begin. So now what is happening over here? See, there are three cases. So you can see there are three photons that are being actually incidented on this particular semiconductor material. This is just a normal p-type or n-type, whatever you want to assume it. It has a conduction band, it has a valence band, right? And you are incidenting a photon having a energy h mu, right? Now three cases are possible. See, there is a band gap energy and there is a h mu. So now h mu can be greater than Eg. This is this particular case. H mu can be exactly equal to Eg and h mu can be less than Eg, right? So what happens when h mu is less than Eg? Then this photon that you are seeing, that are the light that is incidenting on the semiconductor, the photons present in that light don't have the sufficient energy for the electron to be excited from the valence band to conduction band, right? And this is what we want to do, right? So how do we get the current? Just by incidenting a light. So these electrons, so these photons that you are seeing over here, they impart their energies to the electrons in the valence band, and if that energy is sufficient enough, then those electrons goes into the conduction band, and once they are in the conduction band, they are free to move across the material, right? And that's how you get the current. So but if these photons don't have a sufficient energy, then they will just pass as it is. They won't be able to excite the electron from the valence band to the conduction band, right? And what happens for the case when h mu is greater than Eg? So regarding this energy, the only energy that is required to excite the electrons from here to the conduction band is just Eg. So the rest of the energy that the photon has actually, so what will happen, this electron will actually move from here to the a little bit higher energy level, but it will quickly come back to the lowest level or near the EC, because electron likes to stay in the as low energy as possible, right? And the rest of the energy that you are seeing over here, it will be dissipated as a heat in the semiconductor material. Okay, so this is regarding the electron hole pair generation, how the electron hole pairs are actually getting generated. The moment you excite the electron from valence band to conduction band, you get the electron in the conduction band as well as you get a hole in the valence band, right? So just remember this thing. And now we will look at the few terminologies that will actually you will be able to find in a lot of problems, right? So it's better to be clear with those terminologies. So first is regarding the photon flux, right? So what is this photon flux? Photon flux is nothing but how many number of photons you are incidenting on a particular area per second, right? So this is what the photon flux means. And as you can see from this definition itself, the number of photons per unit area per second, what will be its unit? Per unit area means we take everything in the centimeter, right? So it's a centimeter square, and per second means per second over here. So this is the unit of the photon flux. Now why it is so important? Why are we even defining this photon flux? So you should understand that it is telling me how many number of photons I am incidenting on a unit area per second. Now if these photons have a sufficient energy to excite an electron from the valence band to the conduction band, that means what I can actually predict by defining this term, I can actually predict that how many electron hole pairs will be generated. So now sir must have told you that if you have a photon, even though it may have a energy maybe twice or thrice of this band gap, right? But the thing is, this one photon cannot generate a multiple electron hole pairs. I'm not talking about anything regarding the avalanche effect or something. I'm just assuming a normal scenario. The one photon, when it incidents on a electron in the valence band, it only generates a one electron hole pair, right? It cannot generate 5 or 10 electron hole pairs, right? If you want to prove, if you want to see this, then you can refer to the textbooks as well, right? And sir must have told you this concept, I'm damn sure. So now, if one photon is at max can incident one electron hole pair, right? It can just generate one electron hole pair. Now it helps to determine how many number of photons I am incidenting, because it gives me a rough idea of how many electron hole pairs I will be getting by shining this light having, which has the photon of particular energy, right, on top of the semiconductor material, right? So that's why we are defining this term. Now coming to the photon flux intensity. Now this is not only a photon flux, but this is a intensity term, right? So if you talk about the intensity, some sort of energy comes into your mind, right? So what is this photon flux intensity or this light intensity? It is nothing but how much energy you are incidenting per unit area per unit time. Initially it was just number of photons, right? But now it is related to something with respect to energy, right? Now what you are seeing over here, the units are in joules per centimeter square per second. But what people actually do, like sometimes they mention the unit like this, or sometimes they take this energy into seconds, right? They convert it into the power and they just write the unit as watt per centimeter square. So let me just turn on my laser, let me just turn on my pen, right? Correct. So if you look over here, then what it will become, it will actually become joule into second per centimeter square, right? So this is nothing but unit of power, right? So I can just write it as watt per centimeter square, and this is the unit that you will be finding across most of the numericals. Rarely you will be able to see the units mentioned in joule into second, right? So I hope you remember this. Now just a minute, somebody wants to join. Yeah, okay. So now this is the unit of the photon flux intensity, right? And so now what is so special about it? Now what we are actually doing, let's say this is your semiconductor material, right? And let's say you are shining a light something like this over here. Now what actually happens, this intensity, let's say your intensity was, let's say IV0 at the surface, right? You are incidenting the light, right? Now what happens over here at this particular material, this is the thickness of the semiconductor material, right? So at any particular instance, at any particular depth, maybe a distance of IV of x over here, the intensity is not same, because it is a semiconductor material, right? Light has to travel across all the semiconductor material, and sir must have told you that how the intensity changes inside the semiconductor material. It actually decays exponentially inside the semiconductor material over here, right? And you please just remember this formula, because there were few gate questions that were also asked just based on this formula, and if you don't know this, then you won't be able to solve these questions, right? So we have seen two terms. One is regarding the photon flux, right? It was nothing but the number of photons that you are incidenting per unit area per second, right? And we understood why it was so important, because it gives us a rough idea of how many electron hole pairs we are actually generating by incidenting such light, right? And now the next was regarding the intensity, and why this was important, because this intensity will help us in generating the electron hole pairs, right, across all the semiconductor material. So you can see over here, as the intensity is decreasing, as I am going deep into the semiconductor material, my intensity of the light is actually decreasing, right? And if my intensity of the light actually decreases, then that means, let's say this is my point number A, and let's say this is my point number B, right? The number of electron hole pairs, right? The number of electron hole pairs, let's say Na, that I will be generating at point number A, they will be much greater than the electron hole pairs that I will be generating at point number B. And why is this the case? Because my intensity IV of x is actually exponentially decreasing as I am going deep into the semiconductor material, right? So I hope this point is very much clear to you. Now regarding the absorption coefficient, like what is this? So you are able to see there is something e to the power minus alpha x, right? So this alpha is nothing but the absorption coefficient, right? And what is this absorption coefficient actually? So we will look into it, right? So now this is nothing but how effectively your semiconductor is actually absorbing the light, right? The more effectively it actually absorbs the light. What do I mean by that? Let's say this is material A. Let's say this is material A, and let's say this is material B. Let's say and alpha of B is higher than alpha of A, right? So So what does this mean? If I just draw a same amount of thickness over here at particular thickness T naught from the surface, right? What does this mean? The intensity of light that I will be getting. So I will just write it like this: I, intensity of light I will get for the semiconductor material B at the thickness T naught, right? It will be lesser than the intensity of the light that I will be getting in the semiconductor material A at the same thickness T naught, right? And why does that happen? Because my semiconductor material B is having a higher absorption coefficient. It is absorbing the light more efficiently compared to the case number A, right? So now I'll just give you intuitive feeling of absorption coefficient, but now actually let's look at what is actually happening. So first of all, you should note that if the energy of the photon is greater than Eg, then only the absorption is possible. If not, then the light that you are shining on top of the semiconductor material, the material will just act as a transparent for the light, right? It will not absorb anything. So that's why you can see over here, what is the band gap of the silicon. See, this is this blue curve, right, that you are seeing. This is the graph of the absorption coefficient versus the wavelength. Now first question that you will ask me is, why with respect to wavelength my absorption coefficient is changing, right? You should note that hc by lambda is nothing but the energy of the photon, right? As you change the lambda, your energy of the photon itself will change, right? And if the energy of the photon changes, then your absorption coefficient will also change, because what I have told you over here, if your energy of the photon is greater than Eg, the absorption coefficient will be higher, and if the energy of the photon is lesser than Eg, like the material will just act as a transparent, it will not absorb the photon, right? So that means indeed the absorption coefficient is a function of the energy of the photon, and energy of the photon itself is a function of the lambda, right? So that's why with respect to lambda, you can see the absorption coefficient is actually changing, right? So now if I just make a mark around maybe 1.12 electron volt, which is nothing but the band gap of the silicon, right? So you can see we are currently somewhere over here. For the exact band gap of the silicon, right? I'm just projecting this point downward, right? Now what happens, as my wavelength decreases, as the wavelength of the light that I'm transmitting decreases, then the energy of the photon will increase. If the energy of the photon increases, then that means there will be a good absorption for that particular photon, because this E photon will be higher than the Eg now, right? And as you keep on increasing, your absorption coefficient will also increase, and this is what this curve is actually telling you. As you keep on reducing the wavelength, the energy of the photon increases. The higher the energy of the photon, the better the absorption will be, right? And that's why it is increasing like this. Now I will just compare one more semiconductor material. So this is the first that I took, that is our silicon, right? The second one is the gallium arsenide, right? Now for the gallium arsenide, you know what is the band gap? It is something related to 1.4, right? It should lie somewhere over here, somewhere close to here, right? So now it is 1.4 electron volts. Now what is actually happening? What you can see over here, the rise of the absorption coefficient, the rate at which the absorption coefficient is actually increasing, right? Just see how steep this slope is, right? The slope is very high. If I look at the silicon, the slope is lower compared to the gallium arsenide, right? And why did it happen? Why should such be the case? So this is the question that I have asked you over here, and so this is a homework for you guys. Why the curve is so steep for the gallium arsenide compared to the silicon? And I will just give you a hint, right? There is a gallium arsenide and there is a silicon, right? So gallium arsenide is what? Direct band gap semiconductor material, and silicon is what? Indirect band gap semiconductor material. This is the hint, and I hope you will get the answer now, right? So I hope the absorption coefficient is also very much clear to you, right? Now now regarding this absorption, right? So now a very good analogy to understand this thing is related to the why does the glass appear as a transparent, right? So if I just look at this glass, the Eg that you have, the band gap is close to 9 electron volts, right? For silicon it is 1.12 electron volts, and for gallium phosphide it is 2 electron volts, right? Now why does this appear transparent, right? So so whatever light we are getting from the sun, right? So let's say it has E photon energy, right? And now there will be a band gap. See, this glass is there, it has a particular band gap, right? Eg. Now this Eg is too much, it is 9 electron volt, right? And the photon that we have, that we get from the suns, right, they won't be having this kind of energy. So if the energy of the photon itself is lesser than Eg, then I already told you that the material will act as a transparent, right? It will not absorb anything, correct? So that is the reason why your glass actually appears to be transparent, right? And if you look at the silicon over here, right now it is looking little bit like a black, right? So what does this black means? That means whatever light actually I am shining on top of it, right, it is actually absorbing most of the stuff. It is actually absorbing most of the stuff, and it is not reflecting back the same things, right? So that means the most of the stuff is getting absorbed by the silicon. And you know, like if there is any particular object and if it is absorbing most of the light and if it is not reflecting back anything, that object will tend to be look like a black color. It will look like something like black, right? So that's why over here the silicon material that you are seeing over here, it is looking like a black material, whereas for the glass that you are seeing over here, it is completely looking the transparent. And I hope the reason is clear to you, like the you can relate it with the energy band gap, right? And this is the graph that I have taken from the Donald event, right? This just shows you the visible spectra that is present over here, and it just maps, it just mentions the different semiconductor materials and their band gaps. So for example, silicon, as you know, it will have a band gap of around 1.12 electron volts, right? So now it just tells you, like it just tells you what is the lambda, what is the range of the lambdas that you can use to excite this material and can get the electron excite from the valence band to the conduction band, right? So I hope this diagram is very much clear to you. Now let's move on to the next concept of the generation rate of the electron hole pairs, right? So now one of the main things that we are interested is in how many electron hole pairs are getting generated per unit volume, right? Per unit volume per second, right? So this is one thing that we are interested in, like we just want to know how many electron hole pairs are actually getting generated if I shine a light on top of the semiconductor material, right? And what is this? This is nothing but the photon flux intensity that I had just told you, right? And what was its unit? Something like watts per centimeter square, right? Watts per centimeter square, or you can also write it as joules into second per centimeter square, right? So this is how you can also write it, right? So now this generation rate that you are seeing over here, see, I'm shining the light, I'm definitely shining a light on top of the semiconductor material, but not everything will get absorbed, right? See, this absorption coefficient is there, right? Correct? So only, so what is actually happening, I'm shining a light, but because of this absorption coefficient, only certain part of it will be getting the absorbed, and only that part, only that intensity will be used to generate the electron hole pairs, right? So that is what we have written over here. Okay, we are shining a light of having maybe intensity of IV of X, right? So what is this X actually? X is nothing but this thickness of the semiconductor material. So at the surface you have IV of 0, right? So now we are shining a light of particular intensity, right? Now because of that absorption phenomena, only a certain part of that will be used for generating the electron hole pairs, right? So that is why we have multiplied it with the alpha over here. And now if I find, like this is what I have multiplied it with the alpha, right? I have just multiplied it with the alpha, correct? So now this alpha that you are seeing over here, what are its units? The alpha units is per centimeter. It is per centimeter. It is the absorption coefficient, right? And if you just want to see, you can see over here its units are per centimeter, correct? So now if its units are per centimeter, and what I have over here, it's joule into second upon centimeter square, right? Then if I just multiply this two things, then what it will become? Joule second per centimeter cube, right? Now what I have to do, see, this is the joules. What is this joules? Joules is nothing but the energy of the each photon, right? Energy corresponding to each photon. And what I want, how many electron hole pairs are getting generated per unit volume. Per unit volume means per centimeter cube per second, right? This is what I want. So right, this is what I want. So what I have to do, I have to divide it with respect to the energy of each photon, right? The moment I divide it with the energy of the each photon, right? So then you will get what? You will get this per centimeter cube per second, right? So I hope this is clear. By the way, this second is not over here. I'm really sorry. This second should be in the denominator over here. Just a minute. This should be in the denominator. This is not in the numerator. Yeah, right. So what you will get now, you will get the per unit per centimeter cube per second, right? So that's how we got this generation rate, right? How many electron hole pairs are getting generated per unit volume and per unit second, right? And so this is the assumption that we have used. One incident photon of energy greater than Eg yields one electron hole pair, right? It does not matter whether it has the energy 5 times the Eg or 10 times the Eg, right? The rest of the energy is just going to get dissipated in the semiconductor material, right? So I hope so whatever I have written over here, these are the same things that I just explained to you. So I hope you won't forget this formula, right? So now let's move on to the few problems. So whatever we have studied till now, let's solve few problems, and after that we will move on to the concept of the solar cell, right? So now let's look at the first problem for today. Just a minute. Yeah, correct. So now let's look at the first problem for today. So okay, so what is this problem? Calculate the thickness of the semiconductor that will absorb 90% of the incident photon energy, right? So now what they have written, consider silicon and assume that in the first case the incident wavelength is 1 micrometer, and in the second case the incident wavelength is lambda is equal to 0.5 micrometer, right? So I have a semiconductor material, right? I am shining some light on top of it, right? So this is my IV of 0. This is at the surface of the semiconductor, right? And now this is the thickness that I will have. Let me denote the thickness by D over here. So this will be nothing but IV of D at the other end of the semiconductor. Now what they have mentioned, calculate the thickness of the semiconductor that will absorb 90% of the incident energy. So now you already know that this IV of D is nothing but this IV of 0 into e to the power minus alpha times d. This is the formula that we have seen, right? It decays exponentially. Now what they are asking, calculate this thickness d such that this IV of d will be nothing but just 10%, 0.1 times IV of 0. Now why did I write it like that? The 90% of the energy is getting absorbed, so only 10% of the energy, only 10% of the intensity is coming out of the semiconductor material from the other end, right? So this is what I have to write it like, this is why I have written it like that, right? So now if I just substitute over here, right? So this will be nothing but IV of 0 into e to the power minus alpha d is equal to 0.1 times IV of 0, right? So IV of 0 and IV of 0 will get cancelled. What I am left with is e to the power minus alpha d is equal to 0.1. Now do I know the value of alpha? Nothing has been given in the question, but they have given us the diagram on the right side. So the material is the silicon. The wavelength has been given to me, right? 1 micrometer, and in the second case it is given as 0.5 micrometers, right? And we have just seen the curve of the absorption coefficient with respect to the wavelength. So here is my silicon. Here is my silicon curve at a particular wavelength of 1 micrometer, right? This is my 1 micrometer. I will just project this point on this silicon curve, right? And what I will get something like this. This is exactly 100. The absorption coefficient value is 100, right? So what does this mean? The absorption coefficient I have found out, right? So let me just write it. For case 1, my absorption coefficient alpha is equal to 100, right? So now let me write this as equation number A. So what I will do, so put in equation number A, correct? The moment I know the alpha, then it is easy for me to find the value of D, right? So now let's see what happens now. So if I just substitute, then it will become something like e to the power minus alpha, sorry, not alpha, just a minute, e to the power minus 100D is equal to 0.1, right? And if I just take the log on both the sides, right? If I just take the log on both the sides, what I will be left with? I will be left with minus 100d is nothing but ln of 0.1, right? And if I just write 0.1 as 1 divided by 10, right? Then it will be left with, I will be left with 100 is equal to ln of 10, right? There will be a minus term that will be appearing, so that this minus and this minus will get actually cancelled, right? So now this is what we have actually. So now if you just calculate it, right? If you just substitute it, then the value of d that will come out to be, it will be around 0.023 centimeters. So this is the thickness of the semiconductor material. If I use, then from the other end of the semiconductor material, my light intensity will be just 10% of what I was getting at the surface, right? So now let me move on to the case number 2, right? What is case 2? My lambda has been given to me as 0.5 micrometers. So corresponding to this 0.5 micrometers, I have to find the absorption coefficient, right? So corresponding to, let's say my 0.5 is somewhere, just let me see, it is somewhere here actually. I'm just projecting the points on the downwards. This is my 0.5, right? If I just project it horizontally, then you can see it is actually hitting the 10 to the power 4 number over here, right? And this is my absorption coefficient. So for this, my alpha is 10 to the power 4, right? So now again I will use the same equation, right? And let me just substitute everything. 0.1 is nothing but e to the power minus 10 to the power 4d, right? So if I just take log on both the sides, then my d will become what? Ln of 10 divided by 10 to the power 4. So my value of d that you will be getting, it will be close to around 2.3 micrometers. Right? So I hope the question is clear to you. What actually happened, just when you decrease the wavelength of the light by the factor of twice, right? Your alpha actually got increased by the factor of 100, right? And your thickness drastically reduced compared to the case number 1, right? So that is the power of reducing the lambda. You are getting the 100 times benefit in the absorption coefficient, right? So I hope this is very much clear to you. So now let's move on to the second problem, right? So what they are asking in the second problem is calculate the generation rate of the electron hole pairs given an incident intensity of the photon, right? So now this is a formula that we should keep in our mind regarding the generation rate for the electron hole pairs, right? So consider a gallium arsenide at T is equal to 300 Kelvin. Assume the photon intensity at a particular point is given as 0.05 watts per centimeter square. I hope you remember this unit, right? I had just explained it to you few slides back. At a wavelength of lambda is equal to 0.75 micrometer. This intensity is typical of sunlight, for example, right? So now they are just saying us that this intensity that you are seeing, this is the intensity that you usually get from a particular sunlight, right? So now what you have to do, we have to find the G dash, right? So what is this G dash? G dash is nothing but alpha times IV of x divided by h mu. The IV of x that you are seeing, it has been given to me, correct? The h mu value I have to calculate. It is nothing but your hc by lambda, right? I can find it out very easily. And what about the alpha? See, alpha we don't know, right? We have to look at the gallium arsenide chart and we have to see what is the absorption coefficient for this 0.75 micrometers, right? So now if you try to look at it in the previous chart itself, right? So if I just take the lambda somewhere close to over here, right, this is just a minute, yeah, this is where my 0.75 micrometer will lie. And if I just project this point upwards, right, if I just project it upwards somewhere maybe close to here, right, then what I will be getting, I will be getting the projection like this. So this point that you are seeing, it is actually just below this 10 to the power 4, right? So now the alpha that you will be getting for this gallium arsenide, right? For this gallium arsenide, let me just write it, this alpha, if you just calculate it exactly, then it will come out to be around 0.9 into 10 to the power 4 centimeter inverse per centimeter, right? So I hope this is very much clear to you. Now we know the alpha, we have to just calculate the value of h mu now, right? So now how to calculate this value of h mu? Sir must have told you this, right? If I take the E in electron volts, right, this is nothing but my hc by lambda, correct? So I have to take it like 1242 divided by lambda in nanometers, right? So this is the easiest way to calculate it, right? So 1242, and what is the lambda? Lambda has been given as 0.75 micrometer. So this in nanometer it will become 750. So the energy in the electron volts you will get is around 1.65 electron volts, right? So now let me substitute everything in this particular equation, right? So this g dash that you are seeing, it will become what? Alpha is 0.9 into 10 to the power 4 into IV of x. So IV of x has been given as 0.05, right? 0.05 divided by h mu, right? This is hc by lambda. We have already calculated the value of hc by lambda. It is 1.65 electron volt. So 1.65, and for electron volt I have to multiply it with the cube, correct? 1.6 into 10 to the power minus 19. So this g dash value, if you try to calculate, this value will come out to be around 1.70 into 10 to the power 21 per centimeter cube per second. So this is our final answer, and this is what they were actually asking. So just look at the quantity, the amount of the concentration of the electron hole pairs that I'm getting, that is actually generating. The magnitude is around 10 to the power 21 per unit centimeter of volume and per second. So this is a concentration, and typically this is a high number, right? So I hope this is very much clear to you. So now let me move on to the next problem over here, the problem number 3, right? So let's see what this problem is actually asking us to calculate. So a photon flux with the intensity of IV0 0.1 watts per centimeter square, right? Just remember this unit, we have already studied it. At a wavelength of 1 micrometer is incident on the surface of silicon, right? Assume the absorption coefficient. So alpha is fortunately given to me as 100. We don't have to do anything, right? And the wavelength has also been given to me. What is the steady state excess carrier concentration per centimeter cube if the excess minority carrier lifetime is 10 to the power minus 7 seconds? So now you have to think about a formula which relates this excess carrier concentration, right, with the minority carrier lifetime, right? So can I do something? Is there any relation between the excess minority carriers and this lifetime? Of course there is a relation. This delta n will be nothing but GL into tau n, right? I know the tau n, I know the delta n, right? So I can easily find out the value of GL over here, right? So now they are asking us to calculate this delta n over here. So first of all we have to know the value of GL, and we have to know the value of tau n, right? So tau n has already been given to me, but what about the GL, right? We have studied something, their intensity has been given to me. So we have to think about a formula that relates the generation rate with this intensity. And what is that formula? So that formula is nothing but GL is equal to alpha times IV of x divided by h mu. Do I know each and everything in this term? So let me check. H mu I can calculate. This is nothing but hc by lambda, right? And lambda has been given to me. Okay, so I can calculate this thing, right? The alpha has been given to me ready-made. What about the IV of x? IV of 0 has been given to me, right? So I will just write this equation for the surface, right? So, right, correct. So this GL of 0 is alpha into IV of 0 upon h mu. Also let me calculate the value of h mu first. So h mu is nothing but hc by lambda, correct? And if I take the energy in electron volts, then this will become what? 1242, right? 1242 divided by lambda in nanometer, so that is 1000. So this is just 1.24, right? So I know the value of h mu now. So this is my h mu. This is in electron volts, right? So I know the h mu, I know the alpha, and I also know the IV of 0. So I can easily calculate this generation rate. And once I know the generation rate, then I will substitute it in the equation number 1 to calculate the concentration of excess carriers, right? Excess minority carriers. So let me substitute everything over here. So this GL of 0 I can calculate as alpha is 100. What is IV 0? 0.1. And what is h mu? H mu is 1.24. And since it is in electron volts, I have to multiply it with the Q. 1.6 into 10 to the power minus 90. Right? So if you just calculate this value of GL, then this value will come out to be around 5.04 into 10 to the power 19 per centimeter cube per second. right? So this is the value of GL that we have. Now what we will do, let me just highlight it as equation number 2, right? So now put 2 in 1, right? So this delta n will be what? It was nothing but GL into tau n, right? And GL I had just calculated, right? What was its value? 5.04 into 10 to the power 19. And what is the tau n value that has been given? It has been given as 10 to the power minus 7 in the question, right? So 10 to the power minus 7. So this delta n value that you are seeing over here, this delta n value, it will be coming out to be around 5.04 into 10 to the power 12 per centimeter cube. So this is a concentration of excess carriers that is generated at the surface of the semiconductor material, right? So now I just want you to note one more thing. Let me just change the color of the pen actually. Just a minute. Maybe green will be better. Yeah, great. So now what is actually happening? Let me just draw the quick diagram of the semiconductor material over here. So this is how you are shining the light, right? This is how you are actually shining the light. So now you know this intensity is IV0, and if I calculate the intensity at any particular point, this is IV of x, and you know the relation, right? IV of x is what? It is IV of 0 into e to the power minus alpha times x. Correct? So now one more thing that I want you to note is this GL, right? GL is directly proportional to IV of x, right? So since GL is directly proportional to IV of x, I can just from these equations, right? From these equations I can easily write GL of x is nothing but GL of 0 into e to the power minus alpha x, right? What does this mean? This means that the generation rate of the electron hole pairs, right? The generation rate of the electron hole pairs at the surface of the semiconductor will be higher compared to the generation rate of the electron hole pairs in the bulk of the semiconductor, right? So if I just take at this particular point, at this particular thickness, at this particular depth of the semiconductor material, let's say the generation rate is maybe around, let's say 10 to the power 19, right? And if I just take this generation rate, if I just calculate it over here, then this may come out to be something like 10 to the power 21 or something, right? So this will be the difference that you will be able to observing. So the generation rate of the electron hole pairs itself is changing as you go deep inside the semiconductor material. And why is this happening? Because the intensity of the light that is actually causing the generation of electron hole pairs, it itself is actually decaying exponentially, right? So sometimes we will use this equation, like this generation rate itself decays exponentially from the surface of the semiconductor to the bulk of the semiconductor, right? So just remember this, we will be using this in our next numericals as well, right? So now let's look at the problem number 4 over here. So what does this problem asking us, right? So a n-type gallium arsenide sample, just a minute, where is my pen? Yeah, n-type gallium arsenide sample has a minority carrier lifetime of 2 into 10 to the power minus 7 seconds. Incident photons with energy, okay, they have directly given the energy, generates an excess carrier concentration of delta P is equal to 5 into 10 to the power 15 per centimeter cube, right? At the surface of the semiconductor. Determine the incident power required. So this power required, right, since they have not given us any area or something, right, by default we will assume that they are just asking the value of IV0, right? So this is what we have to calculate, right? So now first of all we have to relate two things over here. So excess carrier concentration has been given, right, delta P, it is nothing but GL into tau P. This is what we know, correct? So this is the equation that we should remember. This is given to me, this is given to me, even this is given to me, but GL is not known, so I can easily calculate the GL from here. What is the advantage of knowing the GL? Well, I know one formula, right? What is GL? Alpha times IV0, because we are at the surface of the semiconductor, we are not going deep into it, right? Alpha into IV0 divided by h mu. The value of h mu has been given to me. The GL I can calculate from here, maybe from the equation number 1, right? Then I will substitute it over here, so even I will know the GL over here, right? What about the absorption coefficient? About the absorption coefficient, then the absorption coefficient should have been given in the question. So just note this value, the alpha for this particular numerical, the value of alpha is around 7 into 10 to the power 3 per centimeter. This is given. This is given in the question, okay? So just assume this value. So even the alpha value is known to me, right? So from here I can easily calculate this IV0, right? Only this IV0 is not known in this equation. So let's start with the equation number 1, right? Let me write it as equation number 2. So from equation 1, I can easily calculate GL to be delta P divided by tau P, right? And this value will come out to be something, right? So what will this be, this value? Let me substitute it. Delta P is 5 into 10 to the power 15, and about tau P, what is the value of tau P? 2 into 10 to the power minus 7. So this GL value, this will come out to be around 2.5 into 10 to the power 22 per centimeter cube per second. So this is the value of GL that I know. Let me write it as equation number 3, right? So now from 2 and 3, right? So GL is 2.5 into 10 to the power 22 is equal to alpha. Alpha is what? 7 into 10 to the power 3. IV0 I don't know. We have to find it. Divided by h mu. H mu is 1.65 electron volt. So I have to multiply it with the factor of Q as well. 1.6 into 10 to the power minus 90. So if you just calculate the value of IV0, right? Then this IV0 value, it will come out to be something like 0. Where is my pen? Yeah. It will come out around 0.9428 watts per centimeter square. I hope this is very much clear. So the first part of the question is done already, right? Now this is the answer for the part number A. Correct? Now let's look at the part B. At what distance in the semiconductor does the generation rate drop to 10% to that at the surface? And this is why I gave you this analogy, right? Why even the generation rate will drop exponentially. In the last numerical itself we have derived it, right? Your IV is there, since GL is directly proportional to the IV, right? Even the generation rate will drop exponentially as you go deep inside the semiconductor material, right? So I will use this formula to solve this question now. So what is the formula? GL of x is equal to GL of 0 into e to the power minus alpha x, right? So this is what we have. Now what they are asking, at what distance in the semiconductor does the generation rate drop to 10% at the surface, right? So they are asking us the case when the GL of x is 10 by 100, it is 10% of GL of 0, right? It is just 0.1 times GL of 0, right? So let me substitute it. 0.1 times GL of 0 is equal to GL of 0 into e to the power minus alpha x. So GL of 0 and GL of 0 is cancelled, right? So 0.1 is equal to e to the power, alpha has been given as 7000, right? 7000 times x, right? So from here you can easily calculate the value of x, right? So this x, if you calculate, then this value of x will come out to be around 3.289 micrometers. So at this particular distance the generation rate will actually drop to just 10% of what it was at the surface of the semiconductor material, right? Again a good numerical. It was taken from the unsolved examples of the Donald Demon, right? So I hope this is very much clear to you. And so now we will move on to the next concept, that is the solar cell, right? So now let me just turn on my laser pointer. Yeah. So now you must be knowing like what is this solar cell and all, right? So now how can we technically look into it, right? We just don't want to say, hey, this is a solar cell, we are getting something. We are engineers, we are researchers, right? We have to quantify each and everything, right? So now let's see what is actually happening over here. So if I just take a PN junction, right? If I just take a PN junction, and you know by default, even if I don't do anything, there will be a depletion region inside the PN junction, right? Because of the doping and all, right? Because of the concentration difference between the holes and the electrons, right? So if I just shine a light on top of this depletion region, then what is going to happen? You will get electron hole pairs, right? You will get electron hole pairs, and by default there is a electric field in the depletion region, right? And how to know its direction? So there are fixed negative immobile charges that are present over here, and there are fixed immobile positive charges that are present over here. Since the electric field is always directed from positive to negative direction, so my electric field is actually from the right to the left direction. That has been shown over here. So now what is going to happen? As these electron hole pairs are generated, right, the electrons will be swept in this direction and the holes will be swept in this direction, right? That is why the IL that you are seeing over here, right? What is this IL, by the way? this IL is nothing but the photocurrent. And what is this photocurrent? The current that I am actually getting because of shining the light on top of the semiconductor, right? So that is not the current that you get because of the shining the light on top of semiconductor. That current is nothing but your photocurrent actually, right? So now that is why the photocurrent is shown in the left side over here, right? Now what actually happens as this current flows, right? This current is flowing in this particular direction, right? And what is the role of the solar cell? So let's say you have a solar panel, right? You have a solar panel over here, so let me just draw something, correct? So this is nothing but your solar panel, right? So what is the job? Let's say you want to operate your fridge maybe, right? So this fridge will act as a load. You have to give the power to this fridge to through the solar panel, right? So this load that you are seeing over here, let's say this is your fridge maybe, right? So this fridge will be nothing but it will act as a load for this particular solar panel. Now what is going to happen, since the current is flowing in this direction, right, there will be a voltage drop that will be generated like this because of the flow of current. Just a simple Ohm's law, right? Let's say that voltage drop is VD maybe, right? Now because this VD is there plus VD is there, what is going to happen now? So it is looking something like this. This is my P side, this is my N side, right? I have a depletion region over here, right? And now there is a particular VD voltage that is now being applied across the PN junction, right? So this difference, right? This is what I'm calling you. This is a plus VD, and you just check the polarities. The plus side is actually being applied to the positive, the P-type semiconductor, right? So it is nothing but this voltage drop that is happening across the load, right? So it will be forward biasing my PN junction, right? And because of that forward biasing of the PN junction, apart from this IL that I am getting in this reverse bias direction, I will also get one forward current, that is IF, right? So the direction of IL is something like this. The direction of IF is in the opposite direction, right? So to get the net current, to actually calculate the net current, right, the net current, I have to subtract the IF from the IL, right? This is what I am doing. I am subtracting the IF from the IL. And what is this IF? IF is nothing but your forward bias diode equation, right? I is nothing but, you know, this IS into exponential of QV by KT, right? I'm just ignoring the one for now, right? So you have to just substitute it over here, right? So this is the equation of the current that you are left with actually, right? So this is the current that you have now, correct? So now if you look at the IV characteristics, right? So this is I, right? This is I, and you have a V over here, correct? So now if you just calculate, if you just try to plot the IV characteristics of this solar cell, right, you will be getting a curve which will look something like this. This is what you will be getting over here, right? So now there are two particular cases that are of actually interest to us. So in the first case, like let me just write it, draw it, I mean not draw it, write it. So this is a PN junction that you have, and you have a load over here, right? You have a load over here, and its value is R. Now if I just short circuit this, that means my R is equal to 0. Then whatever current that is actually being flown, right, whatever current that is actually getting flowed, right, so that current I am denoting by ISC, that is short circuit current, ISC, and now its value is equal to IL in this case, right? So now how to make a sense of this equation, right? So now, right, correct, so what is going to happen, because you made it equal to 0, then you don't have any voltage drop. Your VD actually reduced down to the 0 value, right? And whatever current that you will be getting, that is, I am calling it as a short circuit current, right? So now coming to the next case of R is equal to infinity, right? So now what actually happens, what does this R is equal to infinity means? R is equal to infinity means there will not be any net current flow that will be actually happening, right? See, for the net current flow, your complete loop should be there, right? The loop has to be completed. It should be a closed path for the current to be flowing, right, in the circuit. But what I am saying over here, the R is equal to infinity, that means this load is open circuited. If this load is open circuited, there cannot be any net current flow. So that is why I am equating this current to equal to 0, right? And one interesting equation comes up after doing this activity, right? You will get one equation of about the open circuit voltage. This is the equation that you have, right? Correct? So I hope this is very much clear to you. So we will be using these formulas a lot in solving the question. Remember this thing that the ISC is equal to IL over here. So in some of the questions I will put the IL is equal to ISC in some cases. So you should be familiar with it, like why am I doing that, right? So I hope this equation is very much clear to you. And now let's next move on to the new concept, that is regarding the maximum power delivery to the load, right? So now what does this mean actually, right? See, this is my load, right? Correct, this is my load. I want to deliver a maximum power to this particular load, not maximum voltage, not maximum current. I want to deliver a maximum power to this load, right? And what is the power? Power is nothing but your multiplication of V into I, right? And what is the I? I you already know, right? I equal the current equation of the solar cell. We have already calculated it, and if you just multiply V with it, then this is the equation that you will be getting for the power, right? So now if I want to calculate, right, what is the particular voltage at which I will get the maximum power? So this is the IV characteristics of the solar cell, right? So now if there will be one particular voltage for which I will be getting the maximum power, right? Let's say that voltage is Vm, right? And corresponding to Vm I will get a Im, right? So this is the maximum point, this is the maximum voltage, right? So now how to find out this point where I am getting the maximum power? You all know, right? We take the derivative dp with respect to dv and we equate it to 0, right? So this is the same thing that we have done over here, right? And if you just take the derivative of this equation and if you equate it to 0, then you will be left with this equation. Now you can see over here, this equation is still not very simple, right? What you have to do over here, you have to iteratively solve this. You have to iteratively solve this by any numerical method, right? You must have studied some numerical methods, correct? For example, the Newton-Raphson, correct? So these numerical methods you can use to iteratively solve it, or you can use your scientific calci, just put this equation and you will be getting the operating points, that is the value of Vm, the value of Im and the value of Vm over here, right? So this equation will actually help you to solve it, right? And in some cases, in some questions of the unsolved examples, it will actually ask you to calculate this power value, right? So this is nothing but your Vm times Im that you will be getting, right? And how to solve for this Vm and Im? You have to solve this equation iteratively, right? So I hope this point is very much clear to you, right? So now there are few terms that are associated with the solar cell, that is regarding the what you can say, the figure of merit. How will you compare the two solar cells, right? So let me just so these are nothing but the figure of merit. Let me just write it. Figure of merit for solar cell, correct? So you should have something to compare the two solar cells, right? So that's why we generally define this figure of merits, right? And first term that we are defining is the efficiency, right? What is this efficiency? So this efficiency is nothing but how much maximum power, this is the PM, right? PM is what? Vm times Im, and this is what we have seen in the last slide, right? This is what we have seen, this is what this maximum power point is, right? This is your maximum power point. So this is the maximum power that I can deliver to a particular load using the solar cell that is available with me, right? So now how much maximum power that you can deliver to a load divided by how much power, how much optical power you are actually incidenting on top of the solar cell. So let me just draw a quick diagram for you so that it will become very much easier, right? So this is a load that I am trying to drive using the solar cell. This is a light that I am actually shining on top of the solar cell, right? I will be getting some current, right? I will be getting some current, right? So I'm incidenting some power, and from where it is coming? Of course, this will be coming from the sunlight, right? like I am incidenting some input optical power on top of my solar cell, right? And I am actually getting some electrical power that will help me to drive a particular load, let's say a fridge or let's say a TV, right? So if I just take the ratio of these two things, right, that is how much of the maximum electrical power I can get out of my solar cell and how much maximum input optical power that actually I am incidenting on top of my solar cell to drive a particular load, right? So if I just take the ratio of these two quantities, then this ratio is nothing but the efficiency of your solar cell, right? So I hope this efficiency term is very much clear to you. Now let's come to the term fill factor, right? So now what I'm actually doing, see, I know what is the maximum power that I can extract out of my solar cell, right? This is nothing but my PM. Now what is this term in the denominator? What is this VOC into ISC, right? So if you just go into this curve, right? So now if I go to the right and if I operate at a maximum, that is the maximum voltage that I can get, that is the open circuit voltage, right? Then I don't have any current with me over here because the current will be zero. Now similarly from this particular IM, if I go up, I will get a ISC and I don't have any voltage over here. I don't have any voltage actually over here, right? So now what this thing is actually telling you is that this is one extreme of voltage, this is extreme of the current, right? And if I just make multiplication of this VOC into ISC, right, can both of them occur simultaneously? I mean, is it like the moment I have an open circuit voltage of VOC, I will get a current ISC? Of course, definitely not. The what you can say, when you are having an open circuit, there won't be any current flowing, and when you have a short circuit, there will not be any voltage, right? So I know this cannot occur simultaneously, but if I just take the product of this VOC into ISC, and if I take the product of VM into IM, right? If I just take the product of VM into IM, now what is this VM into IM? You can see this VM into IM is nothing but the area of this rectangle over here, correct? And what is VOC into ISC? This is VOC, this is ISC, right? So let me just change the color of my pen, just a minute, in color, maybe red will be better over here, right? So now what is this VOC into ISC? This VOC into ISC will be nothing but something like this whole area, right? So now what is this fill factor? This fill factor is nothing but, if I just take this area of the rectangle, right, area of the rectangle, this VM into IM, and if I just take the area of the whole stuff, if I just integrate the curve of ISC and VOC, and if I take the area and if I just take the ratio of those two areas, right, so that is nothing but your actually fill factor, right? Why the fill factor? You can just think of how much of the total area this gray color rectangle is actually filling up, right? So the more and more area this gray color rectangle fills up out of this total area, the better is the solar cell actually, right? That means I am able to extract more power, right? I am able to extract more power, right, for the same VOC and ISC case, right? So this is nothing but the fill factor. So we have defined the two terms. One is the efficiency and another is the fill factor, right? So now sir must have told you about this Shockley-Queisser limit. I don't want to go into the lot of depth. I just want to add one point, right? So you can clearly see for a particular silicon solar cell, the efficiency is hitting a peak, right? It is hitting a peak of maybe around some 33 to 35%. That is the maximum efficiency that you will get from a particular solar cell. You cannot exceed this theoretical limit, right? But if I just implement a solar cell, will I get this 33 to 35% efficiency? This is the question, right? So now first thing that you should note that the only losses that are assumed in deriving this Shockley-Queisser limits are nothing but your radiative recombination losses. Radiative recombination losses, right? There are no other factors that were actually taken. So for example, if this is my solar cell, right? Let's say this is my solar cell. Now if I am incidenting some light, right, some of the light will also get reflected back, right? It will also get reflected back. So that light will not contribute to anything, right? So that is one case, like some reflection will also occur, and because we are correcting the load and all, right? we are connecting certain load over here, so there will be some series resistance also that will actually come up over here, and this will just reduce the efficiency, right? And if you just try to design it practically, then the efficiency that you will be getting, it will be close to around some 10 to 15%, right? Not a very good number, right? So I just wanted to add this point, and rest of the Shockley Quasar limit, I'm damn sure sir must have covered it in a very nice way, right? So now coming to the solar spectra, right? Again sir must have told you this, like how the solar spectra actually looks like, and why we have 2 3 curves over here. Like this is regarding to the air mass 0, right? This is regarding to the air mass 0, this is regarding to the air mass 1 concept, right? And again this thing, so this curve sir must have already told you like why these peaks are occurring over here. These are with respect to the absorptions that are happening in the atmosphere and all, right? And with respect to this curve, why I took this curve over here, because you can see in somebody says, right, if you have a solar cell, let's say you are getting an efficiency of n1. Now what you can do, you have a solar cell, right? Correct? You can actually use an optical lens, right? You can actually use an optical lens to uh, to concentrate most of the light on top of this solar cell actually, right? So this is my optical lens, and this is my solar cell, right? So what will happen because of this, like most of the light, right, it will get concentrated on top of the solar cell. And what I expect, if I increase the intensity of the light that is shining on top of my solar cell, the more number of electron hole pairs will be generated, and more the number of electron hole pairs that are actually generated, the better my solar cell is actually, right? So I intuitively I hope that my efficiency will actually increase, right? So this is what this graph is actually showing you. This C is equal to 1 and C is equal to 1000. This 1000 is nothing but the 1000x improvement in the intensity of the light. So if I improve the intensity of the light by the factor of 1000, I just want to check how much improvement I am getting with respect to efficiency, right? So now if you look for this silicon, right, on the x-axis you have a band gap of the silicon is same, right? And on the y-axis you have a efficiency. If you take for this particular silicon, right, then for C is equal to 1 case, for C is equal to 1, I had efficiency of maybe around 28%. Now if I use the C is equal to 1000 case, right, then that efficiency, you can see it is close to around 36%, right? So the improvement in the efficiency that you will be getting, even if you make the intensity of the light 1000 times, right, it is just small, right? It is around just 7 to 8%, but still it is very good, because at least you are able to increase the efficiency of the solar cell, right? And have you increased the area? You have just inserted a lens on top of the solar cell, you have not done anything else, right? So I hope this is very much clear to you. Just wanted to give you a rough number, like if you just, even if you put the optical lens on top of the solar cell, how much efficiency is actually getting improved, right? So I hope this is very much clear to you. And now we will solve few problems based on the solar cell, right? So now let's look at the first problem. So again it has been taken from the exercises of the Donald Newman, right? So now let's look at the problem number 5. Just give me a second, right? Yeah. So now what is this problem asking us? So it is telling us, consider a gallium arsenide PN junction solar cell. It is a gallium arsenide, not a silicon one, right? Okay. Solar cell with the following parameters. Na is equal to 10 to the power 17, Nd is 2 into 10 to the power 16. The diffusion coefficients have been given to me. The tau n has also been given and tau p has also been given to me. Assume a photocurrent density of Jl is equal to 20 milliampere per centimeter square is generated in the solar cell. And who is responsible for generating it? I am shining some light, right? Maybe a sunlight or something. So now calculate the open circuit voltage. Okay, so first of all I know the formula of the open circuit voltage over here, right? So this is my open circuit voltage that I have. Let me see if I know each and everything. See, this Vt is nothing but Kt by Q, right? I already know this. What about the IL? See, IL I know. I don't know, but JL I know, right? So what if I do this? I can write this equation as Vt ln 1 plus JL by JS. Instead of writing it by IL by IS, I can easily write it in terms of JL by JS, that is the current densities, right? Now I know the value of VT, I know the value of JL. What about the JS? No, JS has not been given to me. Can I calculate the value of JS? Of course I can calculate, because we have studied what you can say, the reverse saturation current density, right? We have seen the formula in the case of the PN junction diode, and this is a formula that we have with us, right? So now if I use this formula, do I know rest of the stuff? So by the way, one thing that has not been given is the Ni, of gallium arsenide. So the Ni of gallium arsenide, right, it is 2.1 into 10 to the power 6 per centimeter. Okay, so this is what has been given to me, right? So now, okay, Ni I know, Q I know. What about the Dn? Dn has been given to me, Dp has been given to me, Nd has been given, Na has been given. But what about the Ln and Lp? Ln and Lp, they have not given us directly, but can I calculate it? Of course I can calculate. What is the formula for the diffusion lengths, right? So this Ln will be nothing but root of Dn times tau n, right? And Lp will be nothing but root of dp times tau p. Do I know dp and tau p? Of course I know the dn and dp. What about the tau n and tau p? See, tau n has been given to me, tau p has also been given to me. So everything has been given to me, right? So now let me substitute over here. Root of, what is the value of dn that I have? 190. What is the value of tau n? 10 to the power minus 7, right? So now, correct. So this is the value of ln that I have. And what about the Lp? What is the value of dp? 10. And what is the value of tau p? 10 to the power minus 8. So we just calculate the value of ln, right? So it will come out to be around 4.36 into 10 to the power minus 3 centimeter. If we calculate the value of Lp, then this value of Lp will come out to be 3.16 into 10 to the power minus 4 centimeter. So now I know each and every stuff to calculate the Js, right? So we will substitute everything and we will try to calculate the value of Js, right? Just a minute. Yeah. So what is the value of Js? It is nothing but Q. Q is nothing but 1.6 into 10 to the power minus 19 into Ni square is there, right? 2.1 into 10 to the power 6 the whole square into Dn. What is the value of Dn? 190. 190 upon Ln. What is the value of Ln that I have? 4.36. 4.36 into 10 to the power minus 3, right? Into Na. What is the value of Na? 10 to the power 17. Correct? Now the next thing is dp. dp is 10. 10 divided by Lp. What is the value of Lp? Lp is 3.16 into 10 to the power minus 4. Correct? And the next stuff that I have with me is Nd. What is the value of Nd? Nd is 2 into 10 to the power 16. 2 into 10 to the power 16, right? So now if we just calculate this value of Js. So what is the value of Js that you will be getting? So the Js will be coming close to 1.424 into 10 to the power minus 18 ampere per centimeter square. So this is the value of Js that I got. Now I will just substitute it in the equation number 1. What is the equation number? What is the equation number 1? VOC is nothing but Vt ln of 1 plus JL by JS. Correct? So now I know each and every stuff. Let me substitute everything. The VOC is nothing but 0.0259 ln of 1 plus, what is the value of JL that has been given to me? 20 milliampere per centimeter square, right? 20 into 10 to the power minus 3 divided by 1.424 into 10 to the power minus 18. So this is what I have with me. Now what is the, if I just calculate this value, right, the open circuit voltage will come out to be around 0.9629 volts. I hope this is very much clear to you. Now we have solved the first part of the problem, right? Let's look at the second part. Determine the ratio of the open circuit voltage to the built-in potential. So, okay, we have to calculate the built-in potential also, right? So now let me try to calculate it, right? So let me just write it, part B. Correct? So now VBI is nothing but the built-in potential KT by Q ln of Na and D upon Ni square, right? So this VBI will be nothing but 0.0259 into ln of Na and Nd. Na into Nd is what? Let me just check it quickly. Na is around 10 to the power 17. Nd is 2 into 10 to the power 16, right? 10 to the power 17 into 2 into 10 to the power 16, correct? Divided by Ni square. So what is the Ni? Ni is nothing but 2.1 into 10 to the power 6 whole square. So if you calculate this value of VBI, right? This VBI value, if you calculate, this will come out to be 1.232 volt. A huge built-in potential, right? Greater than 1 volt. So now in the question, they are just asking us to determine the ratio of the open circuit voltage to the built-in potential, right? So we just have to divide these two stuffs actually. So now they are just asking us the ratio of VOC by VBI. So what was my VOC? 0.9629 upon VBI was around 1.232 volts, right? So this ratio, if you calculate, this will come out to be 0.7816. So this is the ratio that they were asking us to calculate. Okay. So I hope again this numerical is clear to you. Not a very tough, not very easy, like a little bit lengthy numerical, right? So I hope this is very much clear, and that's why sir must have told you, just do not forget these formulas even if you move ahead of this course, because we studied this formula I guess in the week 3 or week 4, and now this is the week 10 that the live session is going on for the week 10, but still we are using this formula, right? So please do not forget this formula at any point in your time, right? So now we will move on to the next problem, that is the problem number 6, right? A 1 centimeter cross 1 centimeter silicon solar cell has a saturation current of 1 picoampere. This is 10 to the power minus 12 amperes, right? And is illuminated with the sunlight, yielding a short circuit photocurrent. Short circuit photocurrent, that is your ISC is equal to IL, right? Is equal to 25 milliamperes, right? The maximum output power is 12 milliwatts. So this is PM. This is Pmax is equal to Vm times Im. It has already been given to me, right? So now assume power of the sun to be 100 milliwatts per centimeter square. What is the approximate fill factor, right? So what is the fill factor? This is a fill factor is nothing we have already seen, right? The Vm times Im divided by VOC into IS. Vm into Im I already know. This value I already know, right? Now the next stuff that is remaining is regarding the open circuit voltage and the short circuit current. The short circuit photocurrent has already been given to me. The stuff that is remaining is this VOC. Now we have to find the value of VOC, right? So let me use the formula. What is the VOC? Vt ln of 1 plus IL by IS, right? This IS has been given to me. What is this IS? 10 to the power minus 12 ampere, right? Vt I know, correct? Do I know the IL? Of course I know the IL. The short circuit photocurrent is there, like the IS is equal to IL and it is given as 25 milliampere. So I will calculate the VOC from here. After getting the VOC from here, then I will substitute it over here to get the value of fill factor, right? So I hope this is very much clear. VOC is what? 0.0259 into ln of 1 plus IL is 25 milliamperes, right? Divided by IS. IS is what? Picoamperes, 10 to the power minus 12. So if you calculate the open circuit voltage from here, right, then this value will be coming out to be 0.6201 volts, right? So now let me substitute everything in the fill factor, right? So fill factor is what? Vm times Im. This is 12 milliwatts, correct? Given in the question. VOC is 0.6201. ISC has been given to me as 25 milliamperes, 25 into 10 to the power minus 3. So this fill factor value, if you calculate, then this value will coming out to be very close to 0.074, and I can approximate it as 0.8 actually, correct? So let's see what is the answer that is matching. So this 0.8 is the correct answer actually. I hope the question is very much clear to you. A very easy question, right? No tricks. So now let me move on to the few questions that were asked in the GATE exam, which are based on the solar cell concept that we had just seen, right? So let's solve them. So the first problem from here is a solar cell that came. So the problem came in 2016 GATE exam. A solar cell illuminated uniformly with a solar light of power 100 milliwatt per centimeter square. The solar cell has an area of 3 centimeters square and a fill factor of 0.7. The open circuit voltage is 0.5 volts and the short circuit current is 180 millivolts. The maximum efficiency of the device is. Okay, so let's start from the thing that they have asked us. The maximum efficiency of the device. So what is the maximum efficiency? It is nothing but PM divided by Pin. And what is this PM? Vm into Im divided by Pin. Right? So we have to get this value. So the Pin that you are seeing, see, this is the intensity. This is the intensity. The moment I multiply this intensity with this area, I will get the power, right? So let me just do it very quickly over here. 100 milliwatt per centimeter square. If I multiply it with 3 centimeter square, the area will get cancelled, and what I will be left with is Vm into Im is around 300 milliwatt. Correct? So this is what I am left with now. Now to calculate the efficiency of the device, like I first have to get this value Vm into Im. Right? I will have to get this value, and so from where I will get it. So one more thing has been given to me, that is a fill factor of 0.7. Right? So what is this fill factor? Let me just write the formula of it. Vm times Im upon VOC into IS. Correct? This has been given to me. So now Vm into Im will be what? The fill factor times VOC into IS. Correct? The open circuit voltage has been given in the question. The short circuit current has also been given in the question. The fill factor has also been given in the question. So I can easily calculate the value of Vm into Im. Right? So let me calculate it. Vm into Im will be what? Fill factor is 0.7. Open circuit voltage is 0.5. The short circuit current is 180 milliampere. Right? So now if you calculate this value of Vm into Im, right? Just give me a minute. Yeah. This Vm into Im value, it will come out to be around 0.063. Right? And what will be units? Units will be in terms of watts. Right? Because it's a product of V into I. So I will substitute it in the equation number 1. Right? This is 2. Correct? So from 2 and 1. Right? Eta will be what? 0.063 divided by 0.3. So this will be coming out to be around 21%. So this is the efficiency that they were asking for. Again, a good question, right? They are using multiple formulas. We have to combine multiple formulas to arrive at this efficiency, right? A good question. So 21% is the final answer. Now let's move on to the problem number 8, right? So now what they are asking, now this is a little bit tricky problem, right? So now it came in the GATE exam 2020. PN junction solar cell of area 1 centimeter square uniformly illuminated with this 100 milliwatt per centimeter intensity has the following parameters. So the efficiency has been given to me. Open circuit voltage is given. The fill factor is given. The thickness is also given. The charge of an electron has also been given. The average optical generation rate. So they are asking us the average optical generation rate, right? So now let me just quickly draw a solar cell over here. So let's say this is my depletion region, right? And I'm hitting a light, right? H mu energy, right? I'm hitting a light over here, right? And I'm assuming that throughout this depletion region, my GL will be constant. My GL will be constant, right? I'm assuming it, because if it was changing, they should have mentioned it in the question itself, right? I will be assuming that my GL is equal to constant, right? So now GL is what? GL, what are the units of the GL? Per centimeter cube per second, right? Per centimeter cube per second. This is the concentration of electron hole pairs that are actually getting generated, right? And because of the what you can say, because of the electric field that will be present in the depletion region, I will be getting the current as soon as these electrons and holes are getting swept in the opposite direction, right? So now what will happen? So since the GL is constant, right? Sir must have told you this, right? While deriving the equation of the photodiode, the total current density, sir must have used this equation over here, right? If my GL is not changing with the distance, right? If I just take a strip of the dx, width, right? And if I move this strip from this 0 to t, if I move it from the 0 to t, right? then what is going to actually happen, that this GL, since it is not changing, actually it will come out of the integration. Wait, I just made a mistake. Just a minute. Mm, See, no, this is not correct. Wait, this diagram is not correct. Why? I will tell you the reason. Just a minute. See, this is my depletion region, right? This is just the length of the depletion. This is not the thickness, right? The thickness is actually this. This is the thickness. So my strip that I am taking, it should be like this. I had taken the vertical strip. And the absorption is happening vertically. The decay will happen vertically, right? Not something like this, because I'm not shining the light from here. So sorry for that, but I have to take a horizontal strip, not a vertical strip, right? So I'm shining a light like this. This is h mu, right? And this is what? This is my dx. So if I move this dx from this 0 to the thickness of this depletion region over here, right? And if I integrate it, then I will get this GL will come out, because I am assuming it as a constant, right? And this GL will be constant, and what I will be left with, GL into integration 0 to t is the thickness, right? Into the dx, right? So this GL will be there, and into this thickness, this GL into t, this t will come out actually, and this q was already here, right? So this is what I got actually. The current density is now nothing but q into GL into w. W is nothing but my thickness, right? So now they are asking us to calculate the average optical generation rate, right? So if I use this equation, then what I have, GL is q into GL times thickness, that is t. So the thickness I already know, the value of q I know, the JL, right? The JL, let me check the JL, like whether I know the value of JL or not. See, the JL has not been given directly. I am the one who is going to find this JL, right? And the moment I find this JL, then I will be easily able to find out this average optical generation rate. Now you will ask me the second question, how to find the value of JL over here, right? So how to find out the value of JL? So now we have been given many equations in the over here, right? So now we will be using all these equations. So the first thing that they have given us is the efficiency. The second thing that they have given us is the fill factor, right? So if I write the equations for the efficiency, it is nothing but Vm into Im divided by P into 100, correct? The fill factor, right? So the fill factor is nothing but my Vm into Im divided by ISC into VOC, correct? So this is what I know. Now what if I do this? This Vm into Im, right? This Vm into Im has not, I don't have to do anything with it. So I will just write Vm into Im as FF, that is a fill factor, into ISC into VOC, right? So let me write it as equation number A. Let me write it as equation number B. So what I will do, I will substitute the value of Vm into Im, that is I will get from equation B into the equation number A, right? So my eta will be what? Fill factor into VOC into ISC, and divided by what? It will be P in into 100, right? Now let me check whether everything has been given to me. The fill factor has been known. To me, right? Then fill factor is given. You can see the P in value. Even the P in value I can easily calculate, right? The P in has also been given to me, correct? Now what about the VOC and ISC? The open circuit voltage has been given to me, right? The open circuit voltage has been given to me. Open circuit voltage is given. The efficiency is given. So from here I can calculate the value of ISC. Now, but I don't want ISC, I want the value of JL, right? So I want to get the value of IL over here. Now how to get this value? Now, is there any relation between the IL and ISC through any particular formula? Yes, it is there. The open circuit voltage is what? Vt into ln of 1 plus IL by IS. IL by IS, correct? IL by ISC, right? So now just let me take it. Okay, so there was a confusion from my side. So this is not the ISC, right? This is just the IS, right? So we don't have to even use this formula at all. We don't have to use this. In our case, IL is equal to ISC. See, just like in the previous questions, just a minute. Just like in the just like in the previous questions, right? This ISC was equal to IL, right? So again, we have to do the same thing over here. This IL will be nothing but it will be actually equal to ISC only. So the moment I find the value of ISC, I know the value of IL, and the moment I know the value of IL, I can easily find out the value of GL actually, right? So that's how the question will be proceeding ahead. So now this eta, right, will be what? The fill factor has been given to me. Okay, I will do one thing. Maybe I should write the ISC on the left hand side, and everything should be taken on the right hand side. I guess this will be eta into PN divided by the fill factor into VOC into 100, right? So what is this efficiency given to be? 15. The P in is given as 100 milliwatts, right? Into the area has also been given to be as 1 centimeter square, right? Divided by the fill factor has been given as 0.8, open circuit voltage given as 0.7, right? Into 100. So this ISC value, if you calculate, this value will come out to be around 3 divided by 112. 3 divided by 112 ampere, and this is my IL, right? So now what is this IL equal to? So this J, so the formula that I had was JL is equal to Q into GL into T, right? So now if I want to get rid of this J, then I have to multiply it with the area. IL is nothing but Q times GL into thickness into area, right? So this is a formula that we have with us now. So now let me substitute everything over here, right? Let me check if I have any other extra space or not. Yes, I have extra space. Q into GL into thickness into area. So IL is what? 3 divided by 112. Q is 1.6 into 10 to the power minus 19. GL value I have to find it out. What is the thickness that has been given? 200 micrometers. 200 into 10 to the power minus 4. And what is the value of area? So the area they have given to me is 1 centimeter square. 1, right? So now the only term that is unknown in this equation is the value of the GL, right? So if you find out the value of GL from here, then the value of GL will come out to be around 0.84 into 10 to the power 19 per centimeter cube per second. Just a minute, per second. So this is the value of GL that we have. Now let's check whether this actually matches with the option or not. Yeah, correct. So we have the option over here, 0.84 into 10 to the power 19. So this is the correct answer. I hope this question was clear. Again, a little bit tricky numerical. We had to use a lot of formulas, right? And the tricky part was actually using these two equations. This was the tricky part. Like you should have been this should have been clicked in your mind. Like we have to use these equations while solving the question, right? So I hope this part is very much clear to you, right? So we'll take a very short break, and after the break we will resume the session. Thank you. Yeah. Yeah, just a minute.